In this talk, I will show you the preliminary results of the integration between satellite and ground-based measurements to try to improve the volcanic ash estimation and also the eruption characterization. This is the outline of the presentation. First, I will show you briefly the aphorism project in the framework of which this work has been realized. Then the test case considered for this work. Then a description of all the measurements available. Then the integration and also conclusion. About the aphorism project, aphorism is an FP7 project that aims to develop innovative products to support the volcanic and seismic crisis. It will provide new improved products in terms of accuracy and quality of information. The core of the volcanic part of this project is the MESA procedure that will exploit the complementary between a geostationary and polar satellite sensor, and is based on geostationary severe measurements. And the basic idea is to continuously improve the severe ash estimation by using polar and ground-based measurements. Here you can see the maze temporal flow diagram. For every 15 minutes, the severe measurement is integrated by the polar or ground-based measurements. The integration is realized by, at first, spatially collocated the measurement and then process all the data. The procedure will be applied to three recent eruptions: the Eyjafjalla 2010, Grímsvötn 2011, and the Etneo eruption from 2011 to 2014. So let's start with the first test case considered, that 23 November 2013, and this is a brief description of the eruption that starts at 9:30 and ended 1 hour later. And this paroxysm has been detected from the geostationary severe, from the polar MODIS instrument, and also from the ground-based radar X sensors. In the table here, you can see the time of acquisition of different measurements, and here the ash parameters estimated by using the different system. So let's start with the description of the ash estimation by using the geostationary severe measurement. Severe is on board the Meteosat, a second generation satellite, and it is a multispectral sensor with a spatial resolution of 15 kilometers square at Etna latitude. Here, this is a brightness temperature difference images computed by the difference between the brightness temperature at 11 microns and 12 microns. Here you can find the Sicily. Believe me, this is the Sicily. And here you can see this dark signal here is the signal of the volcanic ash emitted by the volcano. The estimation of all the ash parameters, the aresoptical depth, effective radius, and also mass is obtained by using a real-time and simplified approach named VPR that need in input only the volcanic cloud altitude. So in the first guess, the volcanic cloud altitude is computed by comparing the brightness temperature at 11 microns of the satellite image dark pixel with the atmospheric temperature profile of the nearest WMO meteor station of the area of interest. This is an example of the estimation of the altitude of the volcanic cloud We found dark pixel in this image at 10 UTC, in this severe image, and we found a brightness temperatures of about 49 degrees that correspond to an altitude of about 10 kilometers. Because we were able to find the dark pixel only in this image, we use this cloud altitude for all the severe image processing. So these are the results that we obtained from the severe images. Here you can see the total mass, the trend of the total mass. This is the mean effective radius, and this is the mean aerosol optical depth. And here the plot of these different quantities. And also the size distribution for different times that, as you can see, are all centered around 5 microns. These are all the results that we are, all the information that we are able to give if no other satellite or ground measurement are present. But yes, as I told you before, this eruption has been detected also by MODIS and radar. About MODIS, that it is also multispectral satellite system with 1 kilometer square of spatial resolution. The volcanic cloud has been detected at 1245 UTC. Here you can see an RGB image where this is the signal of the volcanic cloud. The ash parameters have been computed by using the same approach applied to the severe measurements, and these are the maps of ash, effective radius, and aerosol optical depth. What it is important to note is that in the thermal infraspectral range we are able to detect and also retrieve the particle between 0.5 to 10 microns, to 10, 15 microns, not more and not less. And okay, these are the system that the Radar X ground-based system installed in Catania airport, that by using these measurements we are able to retrieve many ash parameters, S8 of the airborne particle, the ash mass loading, the particle size distribution, and also the ash concentration. And this system, the eruption has been detected from 940 to 1030. Here you can see the raw measurement. This is the signal detected by the Radar X. And these are all the estimation of the different parameters for this sensor. Here you can see the volcanic cloud altitude that ranges about 3 to 10 kilometers. Here you can see the ash mass. What it is important to note is that the maximum value detected by the Radar X is about 1,000 times higher than the maximum value retrieved by the TIR sensors. And here you can see the vertical section that show the particle diameter of the different particles. And here also the size distribution. Note that the system is able to detect and also to retrieve particles between 10 microns and 2 millimeters, 10, 20 microns to 2 millimeters. So all this part of the particle size distribution is obtained by a model extrapolation. So, okay, let's go on the integration between measurements. Let's start again from the maze temporal diagram. As you can see here, I inserted all the measurements we have for this test case for the different times. And for the different times, the measurements are first spatially collocated, then pre-processed, yes, and then integrated. About the collocation, the spatial collocation is needed because we needed to take into account of the image, of the satellite parallax. Here this is an example. in which you can see here, this is the contour of the ground radar estimate, and this is the severe estimation, and this is before and after the parallax compensation. This compensation gives us an idea of the of the cloud altitude. So we computed the cloud altitude by taking into account of this effect. And this is the procedure that we apply. At first, we interpolate the severe data into the radar grid. Then we realize a cross correlation, and we estimate this displacement vector. And by knowing the geometry of the satellite, we are able to retrieve the volcanic cloud altitude that in this case it is about 8 kilometers. The same system has been applied to the other radar images and also to the MODIS and the severe image. Yes, as you can see, the altitude estimation compared with the first guess altitude as an estimation by using the dark pixel. This point here has been computed by comparing the wind speed computed by following the severe ash center of mass and comparing this value with the NSEP profile collected in the same area in which the plume insists. In the same preprocessing phase, we try also to give an information of the volcanic cloud thickness, because in the thermal interspectral range we are not able to give information of the volcanic cloud, volcanic thickness, and this is mandatory if we want to compute the volcanic ash concentration. So here you can see the isoline that represent the distribution of the particle size, function of altitude, for different distances in the volcanic cloud. So in this particular case, by knowing the altitude, the altitude of the volcanic cloud computed from the parallax, and by defining a bottom altitude for the finest microwave ash particles, we are able to give a first estimation of the thickness of the volcanic cloud. So this is the integration. By using the volcanic cloud altitude, we compute again the severe ash estimation, and here I also introduced the values of the ash retrieved by the microwave system. The integral of this curve here give an estimation of the total amount of the mass erupted by the volcano. By using the cloud thickness, we are able to compute the severe ash concentration, and you can see here the trend of the ash concentration. And by using this information, the ash concentration, we are able to classificate the severe images, and this can be important for the aviation safety purposes. Here is an example in which the classification is realized by considering the no-fly zone and the non-set procedure zone defined after the Aya eruption in 2010. And finally, using the ash concentration, we can compute the particle size distribution in the thermal infrared spectral range. Here you can see the number of particles per cubic meter in function of the particle radius. And so we are able to extend the particle size distribution from micron to millimeter. Here you can see, here we add the thermal infrared that contribute to the size distribution computed using the microwave system. And note that the model extrapolation furnished was extremely wrong in this case. Let's go on conclusions. The integration between the satellite and ground-based measurements allows to improve the volcanic cloud altitude, then improve the severe ash estimations. The estimate of the volcanic cloud thickness is used to retrieve the volcanic ash concentration, and improve the source characterization by estimating, and we can also improve the source characterization by estimating the total ash mass emitted, and extend the particle size distribution from micron to millimeter. The next step will be to use the Metasat second generation 2 severe data to improve the volcanic volcanic ash altitude estimation by means of the parallax with the Metasat second generation number 3 severe measurements. We wanted to extend the size distribution from visible to microwave using the severe visible channel, and then to validate the total ash mass computing using the deposit of ash collected at ground, and also finally use the result obtained to try to constrain the ash dispersion model. Okay, thank you very much.